Hello friends, welcome to our channel Physics for You. As you can see on the screen, in this video we are going to talk about the electrical conductivity. In the last video we have seen about the thermal conductivity. Now this video will be based on electrical conductivity. So basically what is this conductivity, whether it is electrical or thermal? Conductivity means something is moving from one point to other point, and moreover the conduction itself, meaning that something is or someone is conducting something from or some point one point to other point. So in case of thermal conductivity, we have seen our free electrons present in the metal are only the responsible to carry out the heat energy from one point to other point. That is what we call thermal conduction, or the property or the ability of a material of doing this is known as thermal conductivity of that particular material. Moreover, we are dealing with metal, so of that metal. And here the same is true electrical conductivity. Same is true with this particular today's video also. So electrical conductivity means electric field or something is moving from one point to other point. Moreover, our charge, electronic charge or electric charge is moving, and that charge is conducting some energy from one point to other point. So that ability of this particular material, not all the materials have this ability. We know better, yes, because that's why only we use only copper material for the electrical conduction. So only few metals are having these properties, and that property is known as electrical conductivity. So as we can define electrical conductivity, electrical conductivity is a measure of material's ability to allow the transport of an electric charge. Means the ability of that metal, ability of that material to allow the charge, electric charge, move from one point to other point. That is called electrical conductivity, right? In short, we can say we have the movement of electric charge. So this movement of electric charge is not possible in all kinds of materials, not all substances. So that's why only few materials have ability to do this movement of electron, or they will only allow to this charge, electronic charge, to do the movement within the boundaries of metal, obviously. So that ability is known as electrical conductivity, or in simple language we can say the materials or those materials which are allowing electron to move or from one point to other point, or to conduct the electricity. That is what also called as the electrical conductivity. So generally this electrical conductivity is measured in Siemens per meter. Okay. Moreover, this electrical conductivity is denoted as sigma. It is denoted as sigma. The notation for electrical conductivity is sigma. Okay. And again, one more thing known to us is this electrical conductivity and the electrical resistivity, both are inversely proportional to each other. What is this rho? Rho is resistivity. So one can define like this also. It is the reciprocal of resistivity, but for that purpose we must know about the resistivity. Yes, so let us define resistivity here. So resistivity, it is denoted by rho. So how will you define the resistivity? Resistivity means what? If we have a particular rod, okay, of length L, let us consider, and let us consider its area of cross section is A, and let us take the radius of cross section is small r. Then the resistivity is resistance offered by area of unit cross section per unit length. Resistance offered by unit cross sectional area per unit length, and from this we can find its unit also. So its unit, this resistance we know measured in ohm, right? This area, yes, area measured in meter square, and denominator length measured in meter. So this meter and this meter square, 1 meter will get cancelled, and the SI unit for the resistivity will be ohm meter, right? And now the SI unit for resistivity is ohm meter. So we can write in this manner also for the SI unit for conductivity also. It will be the reciprocal of SI unit of resistivity. Okay, so what is SI unit of resistivity? Just we know ohm meter. So this also can be written as the this reverse manner ohm. This it is also known as mho and per meter. So this mho is nothing but Siemens per meter. Okay, or in case of words we can write like this mho. Ohm we are writing ohm meter. It is for resistivity, right? And for conductivity it is mho per meter, and that mho symbolically can be written as like this, because we know we are writing ohm like this. So it's a reverse reciprocal is assumed to be written like this, and this mho is nothing but the Siemens, again we can call it as. So Siemens per meter is the electrical conductivity's SI unit. So here we have defined electrical conductivity and ultimately the resistivity. Electrical conductivity and resistivity are reciprocals of each other. Okay, right. This is what basic idea about the electrical conductivity. Now let us try to find the formula for electrical conductivity. That is our target. We must know one particular formula by which we can find the electrical conductivity. Not this only. This is what simply the relation between resistivity and conductivity. But we must know again here we must know one of them, either conductivity or resistivity. So let us find the formula for electrical conductivity, sigma only. So for that let us consider a rod or a material or a wire through which some electrons, free electrons are moving, and yes, those electrons we know that they are free to collide with the neighboring electrons and all. So if we are taking the time taken between two successive collisions is tau. It is pronounced like this, tau. So the time taken between is tau, that is free time, and the velocity along one direction is u. Let us consider tau is the time taken and u is the velocity. Then we can write the time as tau is equal to lambda by u. Tau is equal to lambda by u, and what is there? Lambda is mean free path. Again in the last video also we have seen this mean free path means what? The minimum distance between two collisions, right? Minimum distance between two successive collisions. So that mean free path lambda. So therefore we got this tau is equal to lambda by u. Okay, right? Now or in reverse also we can write, or if you have to take the analogy of basic or velocity. So generally what is velocity? Velocity is equal to distance upon time. Okay, basic idea, distance upon time. Now what I am saying, if u is the velocity, then u is equal to x by t, and what is this x? X is a distance. So what is now here minimum distance? In our case it is lambda, and what is time we have taken? Tau. So u is equal to, basic definition, lambda by tau, or that is what we have written in reverse manner, tau is equal to lambda by u, nothing else, nothing new. It is taken only from our basic definition of velocity. Okay, right? So the name it as equation number 1. Now if the applied electric field on electrons of the charge minus e, the charge of electron is minus e, is capital E is the electric field on negative charge minus e, then the equation of motion of electron is given by, we know that the equation of motion. So let us see what is the equation of motion here. So the equation of motion can be written as, how we can write the equation of motion? It is m d2x by dt square is equal to minus e into e. How it is? Again you might got the question. So shall I explain here? Okay, so we have two different forces, and due to that forces, those two forces will be balanced. This is simply the force by Newton's second law. It is force, I will write like this, accelerating force, and this is the electric force. So what is force? We know Newton's second law, mass into acceleration. So mass m, and yes, if x is the displacement, then what will be the acceleration? So d2x by dt square. So left hand side force is this m d2x by dt square. Now what about the left hand side, right hand side, we have minus E into E. So the electric force, we already know that if we have a conductor or a charge particle is moving in an electric field E, then the electric force exerted by the electric field on it will be always, if Q is the charge particle, then FQ we can write Q into E. This is simply the electric force, charge into electric field. Now in our case, what is the charge? It is minus E. And what is electric field? Capital E. That's why this is again electric force on electronic charge minus E into E. So these two forces, force due to electric field and force by our Newton's second law, that is force due to the displacement, and those two forces are equal, and from that we can write an equation. That equation is known as equation of motion. So again we will write this equation as, or just bring this m to that side. So d2x by dt square is equal to minus E by m into capital E. This is what the equation of motion of electric field. Name it as equation number 2. Now if we integrate this equation number 2, what we will get? After integrating, we know that in the left hand side we have d2x by dt square, double derivative, and double derivative and integration are reciprocals of each other, or what we can say the opposite of each other. So that's why if I take one time integration, then one derivative will be cancelled. Therefore left hand side dx by dt. Okay, now right hand side minus E by m, E as it is, and the integration of nothing is there, means only dt. So, or shall I write one more step here? Okay, I will try increase one more step. So here I can write it is d2x by dt square into dt. Obviously we are integrating with respect to time. Okay, shall I write here integrating with respect to time. Okay, now dt is equal to minus E by m, it is constant, E capital, again electric field will be constant, uniform for that particular region, and only dt. Okay, and that's why now the integration of this will be dt will be only t, that is why here only t, and to the left hand side one derivative will get cancelled, therefore dx by dt. And obviously this equation is not a definite integration, that's why we must take one of the integration constant and plus c. This is what integration constant. Name it as equation number 3. Okay, simply we have taken the integration of equation 2 and we got equation 3. Now let us apply the boundary conditions on this. So applying boundary condition means, yes, we know this is how the method to solve the differential equation. Moreover, what is this equation number 2? It is a second order differential equation, and mathematics people might know these things, and yes, already we have seen in case of force, and again in second year also how to solve differential equation. So simply get one particular solution, or it is not again solution, but we have taken one integration, then apply boundary conditions. So what is boundary condition here? At a t is equal to 0, means let us consider within the time instant, means before starting that t is equal to 0. So dx by dt is also 0. That means there is no displacement of electron, and x is what? Displacement. So the displacement is 0, or we can say the constant displacement, and its derivative will be 0. So this is what the first boundary condition. If we apply this boundary condition in equation 3, applying boundary condition in equation 3, so what is that? T is equal to 0 and dx by dt is equal to 0. So dx by dt is 0. So therefore left hand side we have written 0 directly. Minus E by m, E, and this t is also 0, from this t is 0 plus c, and directly we get here that integration constant whatever we have taken, that is simply 0, c is equal to 0. Now again resubstitute that c is equal to 0 in equation 3 and rewrite the equation 3 one more time. So rewriting equation 3, or equation 3 becomes dx by dt is equal to minus E by m et, because this c value now becomes 0. So name it as equation number 4. Okay, right. I hope you got this up to this, right. Now next what we have to do, the average velocity between two collisions. So if we want to find the average velocity between two collisions, then we should talk about the, or we should take the integration of this velocity within the limit 0 to tau, because our time we have taken is tau. And obviously when we are talking about the average, so we should divide that again by the tau. So this is how we can take the average velocity. So the average velocity Again it is denoted by like this, dx by dt is velocity, and above which we have this bar, that means it is for average, is equal to 1 by tau within the limit 0 to tau dx by dt into dt. Okay, so this dx by dt is velocity, but this dt for the integration, right? Now let us substitute this value of dx by dt here and let us see what happens. So after substituting 1 by tau as it is, limit 0 to tau as it is, now what is dx by dt? It is minus e by m capital E into t bracket close dt as it is. Now again in this e minus e by m capital E, everything is constant. Simply we have to take the integration of this t with respect to dt. So taking the integration, so what will be the integration? We know that integration of x is equal to, what is that, x square by 2. Okay, now here we have integration of tau or 0 to tau t into dt. So what it will be? It is t square by 2, but we know here it is definite integration, that's why the limits are 0 to tau. And after substituting the limit, how we are substituting limit? Upper limit minus lower limit. So upper limit is tau, lower limit is 0, that's why no need to worry about this lower limit. It is simply tau square by 2. So that's why I have written here directly tau square by 2 minus e by m, e as it is, minus sign I have written here, and 1 by tau from the first term as it is. So let us cancel 1 tau here and rewrite, and again here you might see this how sir has written like this, because this x dot is nothing but dx by dt. Okay, or sometimes we know this can be written as x prime also. We are generally denoting the derivative by x prime, or in classical mechanics generally we are defining the derivative like x dot. So x dot, and this bar is only for average value. So x dot bar is nothing but dx by dt bar is nothing but this, and after cancelling that tau, finally we got equation number 5, that is x dot bar is equal to minus e capital E tau divided by twice m. So this is what average velocity. Okay, now we have to talk about the current density. So if I, capital I naught, it is smaller I, capital I is current, but if small I be the current density, so let me tell you what is current density. I is equal to current per unit area, that is called current density. Current density, current density, it is generally denoted by J or I. Okay, so if small I be the current density and n, small n be the number of electrons per unit volume, then we have the relation between the current density and the number of electrons and the velocity. It is simply I is equal to minus Jn V bar. V is bar is nothing but our average velocity, that is nothing but minus n E x dot bar. Okay, so what we have to do here, you might got the idea. Take the value of x dot bar from equation 5 and substitute here in current density. So yes, minus Ne as it is, this minus Ne as it is, and the value of this x dot bar, what from where we have taken? We have to take from equation 5. So after substituting that value, what is that? Minus small e electronic charge into E electric field tau mean time and 2 divided by m. Smaller m is what? The mass of electron. So what will get cancelled? Firstly, negative negative becomes positive. This negative negative get cancelled. It becomes positive. So n E into E, small e electronic charge square, capital E electric field as it is, in the denominator twice m is as it is. Now shall I substitute the value of tau? The very first equation, right? So here we have taken the value of tau from equation 1 only. So tau is lambda by u. So after substituting that, what happens? Anything cancel? No, nothing will get cancelled. N E square capital E lambda, and what I have done here again, yes, one more thing, just multiplied and divide by one more time by u, just multiplied and divide by u. For what purpose we are doing this, you will come to know. So after multiplying and dividing by u, the equation does not change, but what happens in the denominator? M u into u square, and this u comes in the denominator. So this is what equation 6. Simply we have multiplied and divided by u, so that doesn't make change in the equation. Okay, now why we are doing this, let us see. Because we know that the half mu square, that is the kinetic energy of the electron, it can be written in case of the thermal energy as 3 by 2 kBT. Here kB is nothing but our Boltzmann constant, T is the temperature. And if we cancel this 2, what simply we can write, mu square can be written as 3 kBT. Mu square can be written as 3 kBT. Why we are doing this? Now you got the question. Yes, obviously, because up to this it was okay. Why you sir, you have multiplied and divided by u? Because we should know our final answer, or our final answer should be in terms of the things or the parameters which are known to us. Now here u, the electronic speed, actually we don't know in case of the conductor, in case of the metal, but we know the temperature, we know the Boltzmann constant. That means we have to convert our answer in terms of the things which are known to us. So we already know that 3 kB is a constant and T is the temperature, because if you are supplying temperature or if you are doing the experiment at the room temperature, then at least you know the temperature. Okay, so mu square can be replaced in equation 6 by 3 kBT. So let us do that. Therefore equation 6 become n capital in the numerator n e square capital E lambda u as it is, in the denominator 2 as it is, and instead of mu square let us substitute this 3 kBT. So after substituting, what we get is n e square capital E lambda u in the denominator, 3 2s are 6 kBT. Equation number 7. And what is this equation number 7? It is equation for current density. Current density. Now we are very close to our final expression, because we know that the current density and our electrical conductivity is related as I is equal to sigma into E. I is equal to current density is equal to electrical conductivity times electric field. Current density is equal to electrical conductivity times electric field, and from that we can rewrite as, because we want this electrical conductivity, so electrical conductivity is equal to current density divided by electric field. So already current density we have in equation 7. Take the value of that and substitute here and get the value of your electrical conductivity. So this 1 by E as it is, and the value of current density, let us substitute as it is from equation 7, n e square capital E lambda u divided by 6 kBT. Now what will get cancelled? Yes, electric field will get cancelled, electric field will get cancelled, and finally we got the expression for our electrical conductivity, which is sigma is equal to small n e square lambda u divided by 6 kBT. This is what electrical conductivity of a metal when we are dealing with metal, right? So yes, this is all about electrical conductivity of a metal. N number of electrons per unit volume, E electronic charge, lambda mean free path, U the average velocity, 6 constant, kB is the Boltzmann constant, T is the temperature. Okay, so yes guys, this is all about electrical conductivity. Even though this video looks lengthier, but yes, this should be completed in one video. That's why I didn't try to make it in 2 videos. So I hope you got this, and if you have any doubt you can post in the comment box. Otherwise, if you feel this is value addition to your knowledge, then like this video, and for more such videos subscribe to our channel, right? Press the bell icon so that you will get the notifications of our next videos, and yes, obviously share with your friends who are interested to learn physics. Thank you guys, we'll meet in the next video very soon with a new concept. Till then, you please take care and keep learning. Thank you so much.